Hi, in this mini lecture I'd like to introduce the demultiplexer as a device which operation is in a way opposite to multiplexer. And let's start with example. And let's imagine you'd like to test 4 different DACs from different manufacturers. Let's denote the first DAC 0, the second DAC 1, next DAC 2, and the next DAC 3. And let's suppose you like to do it on the fly, having the same, to hear the differences with these. And this is the audio signal A from a single source, from CD, let's say. And you are listening, and during listening you like to change the DAC to listen, to hear the differences in audio signal. And of course you must have select lines to select one of 4, and 2 lines are enough. And in the case of multiplexer and their indexes, the significance are put here inside the symbol of Dmax. And similarly, outputs, there are 4 outputs starting from 0 and finishing with 3. These are outputs connected to the inputs of the DACs. Okay, and that's it. You simply put the combination, binary combination, which corresponds to the index of the output, to select it, to be connected to this signal A, 0, 1, 2, or 3, depending on these select lines. Let's denote Y0, let's denote the outputs as Y0, Y1, Y2, and Y3. And select lines as usual as 1, as 0. And the symbol is very similar. It is a flipped version of the multiplexer signal symbol, but be aware that you cannot obtain the multiplexer, I mean the real device, but by flipping the multiplexer. Okay, so let's start designing it. You must design it from scratch using gates, using logic gates. But first, the truth table is needed. So we are constructing the truth table. You've got 3 inputs, sorry, A input, S1, S0. Okay, but because of the simplicity of its operation, I will construct the shortened version of truth table, not having A on the left hand side, but having it on the right hand side, similarly to the case as was in the case of multiplex. And you've got the 4. Let's start with Y0. You can change this order depending on your preferences. That doesn't matter. And you've got 4 rows: 0, 0, 0, 1, 1, 0, 1, 1. And you know that if you select 0 in binary, that means that this signal A will appear on output Y0. So here you've got A here. And in the second row you select output A, output Y1, you've got A here, and here, and here. That's the basic operation, basic cases, yes, 2 and 3. Okay, you've got the Y3 because 3 is selected, select lines, so it's very easy. What about the remaining values in this table? It depends on the realization. So there are 2 cases when there are 1s on the unselected, not selected outputs, or 0s. So the first, let's start with 0s. You've got 0, 0, 0 here, 0, 0, 0 here, 0, 0, 0, 0, 0, 0. But of course there is another possibility to have here ones, yes, in these regions, yeah, here, instead of can be ones. All ones or all zeros, there are two cases. So let's start with this and derive the equations for y's. y0 is equal to s1 inverted times s0 inverted times a. Look at this. If s's are zeros, you got 1 here in this product, and 1 multiplied by a gives you a. So zeros here. For the remaining values of s's, you've got 0 here. So zeros will be present on the output, yeah? On the output y0. y1, similarly, it is a minterm one containing two variables s1, s0, and this is minterm one times a. And similar y2 equals s1 times s0 inverted times a. And y3, please do it by yourselves. Okay, please do it y3. Similar situation. And as for practicing purposes, try to derive the equations when there are ones in the truth table. Okay, it is your task, not mine. And the implementation is the straightforward. If you use AND or NOT gates, you even don't need not ORs. Okay, only ANDs and NOTs are needed to implement multiplexer. In the lab, you will be interested in the NAND implementation, so you should put two bars above the equations, above the products, and you've done. Of course, if you'd like to use the same, returning to our example, if you'd like to have only one, yes, you would like to test only DAX, no the remaining parts, let's say amplifier. So you'd like to have the same amplifier for all three DACs and the same speakers. You would have to use an analog multiplexer, analog, because here you've got the analog signal. Yes, analog signal. Analog is not digital, because after transformation into conversion into analog, you've got 4 analog signals, and you must use a multiplexer, which is in this case an analog multiplexer, analog mux. It is different. It's not the same as digital one, having analog circuitry, not only gates inside, but the operation is exactly the same in the digital version. Simply selected input is put on the output, and here we've got the speaker, amplifier and speaker. Okay, and of course these should be the same, S1, S0 to have it. Yes, if you select, let's say 1, you've got here your signal, then analog counterpart of it is put here, because 1 1. Let's say 0 1 here, and the same sequence. They should be connected together to each other. Okay, and you've got it. And you simply change the DAC by changing the values of S1 and S0 to hear a different version of your sound. Thank you.